If you fancy pausing the video and having a go at this, please be my guest. Otherwise, let's have a go at this. Let's read it first and then take it from there. Right, a particle has a mass of 5 kg, so make sure you highlight the key stuff. It's projected with a velocity of 20 meters per second up a steepest slope of a smooth, so there's no friction, incline at 30% to the horizontal and retreating g as 10 meters per second. Okay, the first question, the normal contact force between the plane. So we've got to calculate the normal contact force between the plane and the particle, the total distance travelled in 2 seconds. Right, let's first of all, which is always a good idea, is to draw a diagram. Here's the horizontal and this is being projected up a smooth slope, a mass of 5 kg. So if I got this particle here, this has a mass, so the weight will be mg, which will be 5 g going down, and this incline is at 30 degrees. Okay, and that's being shot up, so this particle is being shot up here at a speed of 20, so initial speed of 20 meters per second. Okay, there's no other force acting on it other than the gravitational pull coming back down. Now, talking about the gravitational pull, let's have a look at this. Because it's a slope, we treat this slope, this incline, as the plane, and then the other, this will be horizontal plane and this will be running perpendicular to it. So that will be the Rn, contact force, and this one will be, well, that is 30, so this will be 30. Okay, always the case. And then this here on the side will be 30, and the hypotenuse is 5g, so it's 5g cos 30, and this coming down the slope will be 5g sine 30. Always opposite is sine and adjacent is on the side here. That's the hypotenuse. Okay, so now we've got all our forces. We need to find the normal contact force between the plane and the particle. So there's the contact force, Rn is equal to 5. Now g, we could, well, I'm going to write it down, 5g cos 30, and we're going to treat g as 10 cos 30, and you can just put that in your calculator. 50 times cos 30, and that will give you contact force of 25 root 3 newtons, or let's see, can do this to 43.3 newtons is the contact force. Okay, that's contact force between this plane and the particle, so that one's done. B, total distance traveled in 2 seconds. Okay, so since this is going to be a suvat, because there's no other force acting on this, okay, so it's just this force is a constant force, hence constant acceleration. So in scenario B, we're just going to treat with the suvat first of all, SUVAT. We need to know what is the distance traveled, so we want to know what the displacement is. We know the initial speed is 20. We know that the acceleration, yeah, we can find out the acceleration. Just give me 1 second on that one. And the time we need to know after 2 seconds. So let's have a look at the acceleration first of all. Well, the acceleration, where we get force equals mass times acceleration. The mass is 5, so that's going to be 5a, and the only force acting on here, well, it's acting against it because it's coming down as the particle is being shot up. That force here is acting down on it, the gravitational force pulling it down, so that's going to be a minus 5g sine 30. So that's the only force coming down on it. So to get the acceleration, divide that by 5. So acceleration will be, this is my g is 10, so that's minus 10, and sine 30 is a half, so acceleration will be minus 5. Okay, meters per second. So just going to put a line down here and do part B. So we've got U, we got A, we got T, and we want to find S. So I'm going to use this formula, S equals UT plus half AT squared. So the displacement after 2 seconds is going to be 20 multiplied by 2 plus a half minus 5, it's acceleration, and that's 2 squared. So that will be 40. That's going to be half one of those, minus 10. So S, the distance it would have traveled, is 30 meters. Okay, so the total distance traveled in 2 seconds is 30 meters. It hasn't come back on itself, so that's, if that was bigger than that, then we know then it's coming back down on itself. Okay, so we're okay at the moment. Thank you.